Okay, our last but not least speaker is Justin Romberg from Georgia Tech.
Thank you. So, I one more time like to sincerely thank the organizers for inviting me to speak, and I consider it, somewhat of an honor to be the last speaker at the end of such a great meeting. And seeing as, I am the last speaker, I'm going to try to keep things sort of very light and familiar. And so I'm going to talk about, for the entire time, sort of the program which is very familiar to all of us, right? This so-called lasso or L1 minimization problem. And usually when we encounter this thing in the context of signal processing, the way we kind of couch things, the language we kind of use is, okay, we have some, measurements y of some unknown vector x naught that we see through a matrix phi, right? And then, if we believe that this underlying vector is sparse, then if we sort of plug phi and y into this optimization program, then the solution to this thing, we churn this thing, solve it, the solution thing will be good. Where, this word good, we know how to, talk about very carefully in many different ways. Okay, so what I want to do today is, still talk about this, but talk about it in a little different context, right? So instead of just thinking about, okay, I get sort of one set of data y, solve this, and get, my output x naught, and that's the end, I want to think of it more of like what you might call a filtering context, right? So kind of, again, a lot of signal processing situations, what we have is, we're not just interested in solving this thing once, but maybe many times. Right? So instead of just thinking of this lasso as an optimization program, maybe thinking of it as a system which maps, some inputs y, some measurements y, to some outputs x hat. Right? And so the idea again is like, we're going to see you basically be solving the same program, but sort of doing it many times. Right? And so then the question is like, well, so how do we sort of set up and understand this process, and how do we do it efficiently? Right, so we think instead of like more optimization, we think more of this in terms of filtering. So, y comes in, maybe it's a function of time. Maybe the matrix you're using varies as a function of time. And of course, the outputs will also vary as a function of time. And time will be, maybe both discrete and continuous with what we said. Okay, so, we can just kind of loosely call this like dynamical L1 recovery. There's sort of maybe a lot of ways that you can start to think inside a framework like this. I'll just talk about two almost very different ones that have been going on at Georgia Tech over the past few years. Okay, so the first part I'm going to talk about was work that my graduate student Salman Asif just finished. And it's basically a framework for taking solutions to an L1 optimization program. And then if you get, say, something small changes and you get a new set of data, how do you quickly update it? So things that might change are, maybe the signal moves a little bit. Maybe the signal moves a little bit and you have a dynamical system to predict how the signal moves. Maybe I added a measurement. Maybe I changed the weights of something. Like how do I sort of move quickly from the solution of one program to another one, all time staying optimal. Okay, so that's the first part. The second part is almost completely different, but it's more like, we have almost an analog system to put in the middle here. So what we're going to do is instead of thinking this as an optimization program, what we can do is have kind of a neural net inspired architecture that gives us a set of differential equations where we kind of treat this input as initial conditions, and then it settles to the solution of this L1 optimization program, right? And so this has, networks like this have certain like biological motivations. And what we were trying to do is sort of understand like how these dynamical system behaves, right? So here you're really thinking in terms of, again, nonlinear systems of differential equations rather than L1 optimization at the end. Okay, but first I want to talk about fast updating of solutions of L1 optimization. Okay, so here's kind of, the very classical things we learn in the first year of graduate school where we kind of motivate us to look for things like this. Okay, so, if we have sort of a full column rank system, so something which is overdetermined, and we say, okay, knowing nothing about the structure of X, maybe we use least squares to estimate what X is, right? So we say, all right, we set up this variational problem, and then we have this closed form solution, which is computing the pseudo-inverse and applying it to Y. Okay, and so now, first thing you can do, which is kind of obvious, is like, okay, if I get, have the same system and I get another set of data y, I don't really need to do much work anymore, right? If I've already computed the pseudo-inverse or, computed the whatever appropriate factorization to to compute this, solve this system stably, I don't really need to do anything. Basically, all I pay is another vector matrix multiply if I get more data with the same system. The other thing that you can do very efficiently is actually if you can add a row or two or a few to the system. So this is, I guess, what we call recursive least squares. So again, what the sort of basic idea is here, I say I have a solution, or a least square solution to y equals phi x, and then I see, let's just say, a single new measurement now. So I see w equals like little phi transpose x, right? And so how do I quickly update the solution, right? So, you have like phi, sort of this big matrix transpose itself, that changes, right? But you don't have to like compute a new pseudo-inverse from scratch. Like basically it just changes, the hard part of it, this inverse just changes by a rank 1 matrix. And there's sort of a well-known methodology for doing low rank updates and for all these different factorizations in numerical linear algebra. All right, and so particular, what you can say is, okay, look, my new solution after I add this, basically I can write it once I sort of write down, this is, what the new solution would obey in least squares. And if I write down like what that means in terms of the old solution, I can sort of say, okay, look, let me take the old solution and then let me see if I can predict this new measurement I got just by correlating it against this measurement here, right? And then, there's some, what's called a gain matrix that takes the error in that prediction and tells me how to update my answer x now, right? If it matches the kind of, it's perfectly consistent with this new measurement, I don't do anything. If it changes, this tells me how to change, right? And the idea is like, look, if I already have like, phi t phi minus 1 or again some factorization like that in hand, this second part here is really easy. I mean, this is just a scalar. I'm doing 1 over. So really what it's saying is like I'm replacing like solving a system of equations with just a vector matrix multiply. Okay, so, or a few vector matrix multiplies. Okay, so that's, that's nice. So that's the kind of thing that we're after. We add something had, so we get a new set of data, we get a new measurement, how do we quickly update things? So another thing I'll just say is slightly different, the sort of next logical step after recursive least squares is the idea of the Kalman filter. So here, not only are you getting streaming measurements of a signal, you also have a dynamical system which you think, a linear dynamical system which you think models how this thing is moving. Right, so what you could say is, okay, look, if I expect the signal at location t plus 1 to be some matrix times the signal plus some error, and then I measure at each time the signal, you can sort of cram that all into one big linear system which looks like this. I mean, it's kind of bidiagonal, so if I call that A transpose A is kind of tridiagonal, and you can factor it, and when you sort of look at it by inspection, you get this system of equations. So it's not too important what exactly this is, but basically what this says is like, look, how I can do my update here is I say, okay, look, I make a prediction for x. Right? So I expect x to move because I have this dynamical model for it. And then again, I compute kind of a gain matrix which tells me, okay, how do I take this disparity between, what the measurements of prediction was, the measurement I got, and how do I change that to update my answer? And again, everything's linear here, and it's beautiful, and it's kind of one of the bedrocks of statistical signal processing. Okay, so these are the type of things we're after. You have new information, low rank update, new solution. Okay, so how do we do that to solve something like this? So here's our essential program, right? And everything kind of follows through the following realization. So up top is the last. So I've sort of replaced that lambda times the L1 norm of x just with a general diagonal weight matrix. If you like, you can just take the w just to be lambda times the identity. Right, and so then what I can do is I say, okay, look, let me just write down the optimality conditions. What do I need for x star to be a solution to this, right? So you say, okay, well, if you compute the subgradient, 0 has to be in the subgradient. What do I need out of that? Well, here's basically what you need, right? These two equations is what x star has to obey. So what's interesting about this, and what sort of allows us to start to do incorporate this low rank updating, is what we get at essentially at the end of the day is if we kind of know the support or fix the support of the solution, what we have is a linear system of equations for x star and a linear system of inequalities for x star. That's what x star has to be. So in some sense, like x is locally linear. Okay, and so this is a realization and a trick that was actually used like way back in statistics in the 90s with this Lars algorithm. Right? So there the basic idea was, okay, again, if we just replace w with lambda, and what you can do is lambda moves, right? Actually, x star, the solution is going to move in a piecewise linear fashion, and it's going to move in such a way where you can predict like when that system changes, and it changes exactly when the support that you're optimal on also changes. Okay, so that's, again, the optimality conditions. We have a kind of a well-known classical algorithm for when I change the regularization parameter, how to move. And actually what you can do is you can use the same trick to do these updates when other things change, when you have dynamics in your system. So here's one quick example of something we did a few years ago, but it sets the table nicely. So let's say I have, I observe one set of measurements, and I solve this program, right? So I now have the solution x1 hat in my hand. Then I get another set of measurements, right? And I want to solve this second system, right? But the idea here is like, oh, look, I don't expect x1 and x2 to be too different from one another, right? So maybe I don't want to solve this thing from scratch. What you can do is you say, okay, what we're going to do is we're going to slowly map the solution of one of these into the other. And so what you do is you set up, again, this is what's called a homotopy program. So I say, okay, look, I take the two sets of measurements, y1 and y2. I put 1 minus epsilon in front of y1, epsilon in front of y2. Right? When epsilon's equal to 0, I'm clearly at the solution to this first program. When epsilon's equal to 1, I'm clearly at the solution to the second program. Right? And so now the idea is I can actually talk about how the solution to this program changes as epsilon changes. And again, you just do exactly the same thing. You look at the duality conditions. This is exactly the same as the other side, just with this 1 minus epsilon y old and epsilon y new plugged in for y as before. And what you say is, okay, look, I know that I have these linear conditions, locally linear conditions for x, and immediately say, okay, what happens if I change epsilon just by a little bit? Like, how is x going to change? And you compute very quickly, okay, how x is going to change is going to move in this direction. So it's basically, this phi gamma as I take my matrix phi, pull out the columns that correspond to the support that I'm on right now, and say, okay, as epsilon, if I increase epsilon just by a little bit, this is the direction that x is going to move on the support. Right? And the idea is you move in that direction on the support until something changes. Right? And when something changes basically means either one of your active elements goes to 0, or one of your constraints, which means like the support gets smaller, something leaves, or one of these constraints becomes active, which means something wants to come in. So again, you update a gamma. But the idea is like, look, at every sort of step that I make, I can very quickly say when one of the next either constraint will be violated or something will leave the support. It's a simple calculation, really, again, because it's linear. And then to compute this new direction, again, it's just a low-rank update, because I'm either removing or adding a column to this phi transpose phi that I'm doing. So what you're doing is instead of just saying, okay, look, instead of a single low-rank update, what I've broken this down to is a series of low-rank updates, right? One for each kind of segment of this piecewise linear path between the old solution and the new one. Okay, so this is a nice trick. We can, run experiments, talk about when it works. So, some of these are really synthetic examples. Here's like an example where we had a sparse signal and we changed some percentage of the support of it at every time. Here's something where we maybe had one of these classic like wavelet test signals, or two of these classic wavelet test signals, and maybe we modulated what went on here. So maybe we moved the singularities a little bit and waved what went on. So maybe this, as time advances, these wavelet coefficients change slowly. Another thing we did is, okay, we look at a series of 1D signals by taking a slice of an image and moving it down. So then again, if you look at the sort of wavelet transform, as I move down slices of this image, it looks almost the same. Then maybe there's an abrupt change when I hit an edge. So, you do a lot of updates, and then I get something else. So test cases like this, essentially what you can say is if you kind of look at the number of matrix vector multiplies you need, you just to summarize the table, you do better than taking sort of state-of-the-art L1 solvers and warm starting them in kind of the obvious way. So in that sense, stuff like this, it's kind of a good idea if your assumptions about the sort of the path or the difference between the old signal and the new signal is if it is indeed small. Okay, so that's a good trick, and in fact, you can play that trick in many different ways. You can do things like, so instead of just, we just talked about, okay, just, the underlying signal changes. So we phase out old measurements, phase in new ones. Another thing you could do is you could add or remove rows of phi, right? So that's slightly different than what I just talked about. So then maybe the idea is the thing you're measuring isn't changing, right? But you're getting more information about it. or you want to release old information about it. So again, what you do is sort of phase in a row of phi and phase in a new measurement, and again, you trace the path, and it turns out to be linear too. Another thing you can do, which is kind of cute, is in some sense, we say is, okay, look, if I say I want to do some kind of reweighted L1 program, so I want to solve this program and then choose the weights adaptively based on solution and resolve it again, you can actually, like, again, set up these techniques where the difference between these two solutions it's important but subtle in that it's small. You can incorporate kind of a weight change also, just phasing out the old weights and phasing in the new ones, and you get the same type of idea. Okay, so what none of these are, though, or I should stay on this side. No, what none of these are, none of them are really predict and update. They're all kind of like working from an old solution and trying to work out to a new one. All right, so what we want to do things like, maybe the non-smooth version of the Kalman filter is we want to say, okay, look, I don't want to necessarily start at the old solution to my program because that might not really be a good guess for what's going on here, right? Maybe the thing has moved and like I can model that motion, and it's really the error that's going to be small from that model. And so really what we want is kind of a predict and update. And so actually we can unify all these things and add predict and update just by doing something very simple. So what you can do is say, okay, say I want to solve this program, period, and I have a guess for what the solution might be. Right? And so maybe that guess comes from like taking the old guess and applying some FT to it to predict where it's going to move. Or maybe I have some other knowledge about what the solution might be. There's actually like sort of a very simple thing you can do. You say, okay, look, let me just add this as a term in my program. If I carefully choose, so when epsilon equals 0, when epsilon equals 1, clearly I'm going to be solving the program I want to solve. Then what I do is I just choose u very carefully. So when epsilon equals 0, I'm at the solution of this program. And you can just do that very easily as a function of v and the other parameters in the program. Right? And again, all the, you argue this is optimal again just by sort of computing what the optimality conditions for this program are. But it just gives you a nice way to take a guess, compute something based on that guess, and then we can work from your guess to the new solution simply by moving along this piecewise linear path. Okay, so then and here's how you do it. So the direction you move, whenever you're on gamma, you just move along the u vector on this gamma till one of the constraints gets violated, etc. So it's exactly the same as the old, and the point is we can just compute what this new direction is. Okay, so what's one thing we do that. So now, since we have this more general way of kind of taking a guess and then instead of working from an old solution to a new solution, working from a guess to a new solution, we can do things, and this is kind of what motivated our work, like reconstructing from streaming measurements, right? And so this is, kind of what we're after. So, maybe we have a signal which we can write like this. So maybe we have like, the signal is maybe it has a very natural time frequency representation. So what I usually think of these things as maybe being like, what's called like local cosine. So some kind of smooth local Fourier series that you're using to represent the signal. But to make these so that there's no gaps, like these windows, if they're smooth, they kind of have to overlap with one another. Right? So you can think of kind of a streaming system where I have these kind of coefficients arriving in chunks, and I'm using them to build up part of a signal. Right? And then on the other end, so I have another system which is continuously measuring blocks of this signal, right? And maybe these blocks are overlapping, or maybe they're not. But the point is, like, you only need one of these two things to be overlapping to make the solutions coupled as time moves on. Right? So now the idea is, okay, look, I have a sort of a solution over a window. I get a new set of data in. I want to phase out kind of an old solution and phase in a new one. How can I do that in a principled way? Well, we do this, exactly as before. We make some kind of prediction. The prediction may depend on many things. There's some details that take care of boundary effects, but then the idea is you just simply work it in by ramping up this epsilon. Okay, and this is, I'll skip this part, but it's particularly interesting when you make that prediction by taking your old solution and then doing this idea of the Kalman filter. So applying this dynamical system to predict where the thing is going to be next. So again, like a lot of people have written about and looked at this idea of an L1 regularized Kalman filter, but the point here is not so much like how well does this work or what's the issue. We're an algorithm for doing it. Okay, so have an algorithm for doing it. And if you look at the results you get. So here's like a typical test where we say we took a signal and we moved it around. So we just shifted it, and then we added jitters to those shifts. That's why these things aren't quite straight lines. So that was kind of like our predicted, we predicted a shift along a slope and then jittered a little bit. And then you look at like how long does it take you to solve these things. So say in the middle here, this axis is like the number of, say, vector matrix multiplies you need. And this red is like warm starting a state-of-the-art L1 solver. And like down here is us, so it's like a savings of 4 or 5 or 6 just by, again, slowly working in things and tracing along this homotopy path. Okay, so that's sort of one nice framework for incorporating dynamics. So I have a solution of L1 programs. I want to either quickly move from one solution to the next, assuming something small changes, or I want to take a guess at what this one is, possibly based on past data, and I want to work my way from the guess to that solution. And you can do it all kind of with path following, and it can result, again, if your assumptions hold even approximately, it can result in big savings. Okay, so that's one idea. So the second type of body of work is, again, different. So now what we're going to kind of think of is we're going to think of, okay, we have data come in, and instead of having some kind of like digital iterative algorithm for solving this L1 optimization program, what we're going to do is we sort of use that data as a set of initial conditions for a dynamical system which settles to the optimization program. Okay, so the reason we're considering this, or one piece of motivation for considering something like this, is there is kind of a new swath of signal processors that are sort of going back to the future in terms of analog signal processing. So essentially, you can build very low power, approximate, let's just say vector matrix multiplier circuits that have kind of limited accuracy. Maybe you get 2 digits of accuracy, maybe you have limited dynamic range, but the idea is these things can have high bandwidth and only use a small amount of power. All right, so maybe say the bandwidth's 100 megahertz and you have 100 inputs and 100 outputs. What that kind of means is if you have 100 megahertz signal, it kind of means you have 50 million degrees of freedom per second. So you're kind of doing 50 million matrix vector multiplies per second. Right? And so again, they're not necessarily accurate, but a very low power. Okay, and so if you build something like this with some simple feedback, you can actually say, okay, let's say instead of just vector matrix multiplying, say I'm interested in solving, say, this optimization problem. There's actually many optimization problems you might solve. In fact, there's like a very simple generalization we're doing. Instead of taking the magnitudes and adding them up, I just take some function and adding them up. We can, actually come up quite easily with a system of differential equations that we can implement in something like this that settles to this solution. And we're going to talk about, how do we know that it settles in a second. Right? So here the idea is, this is a linear system of differential equations in u and x, and then x is just related to u through some nonlinearity. Right? And so this actual instantiation is called the locally competitive algorithm. It's similar to kind of like many neural net implementations of other optimization programs, which were kind of like a cottage industry in the early 90s. The person, my colleague at Georgia Tech, who started to talk about this a lot a few years ago, he really came about it as kind of a model for part of the visual system, rather than for doing any kind of like computations. But anyway, so you have a system like this. I mean, this T lambda, how does it? It's just related to C. So basically, C is the something like the derivative of this T lambda. So if you're doing L1, this T lambda is just a soft thresholding. And then, to implement this system, you can kind of draw a block diagram that does it quite nicely. I mean, essentially, what you have is you have sort of a set of states that are getting fed in these nonlinearities, and these outputs are getting fed back through, like, basically phi t phi minus I, and integrated back into the state variables. So in some sense, what this looks like is really just almost exactly a continuous time version of iterated soft thresholding. Right? Except, again, there's just continuous feedback as everything's evolving. Right? So instead of like moving in discrete steps towards a solution, you kind of move along this continuous path. Right? So then you have some natural questions, like, how can I really talk about this convergence? And you can get a long way with results in the classic literature, but there's actually a couple complications that don't apply exactly to what we're saying. And then, like, okay, let's say I'm actually trying to solve the last, so trying to recover a sparse signal using L1 message. Can I talk about the convergence speed, or say characterize this path from the starting point to the solution? And yeah, it turns out we can do both of these things. And in fact, our tools for doing this last one, it's nice because they sort of use this restricted isometry property, kind of mirror some of the results that we see for orthogonal matching pursuit and homotopy algorithms for the digital case of solving this. Okay, so let me just talk briefly about what we know about this system. Okay, so first, we have some mild assumptions. We can talk about a sort of a general convergence result, not just for solving L1, but for solving with any nonlinearity. If we just make a few assumptions about what that nonlinearity is, and they're very mild. Basically, what it says is, okay, we have a dead zone between minus lambda and lambda. It has to be continuous. There can't be a jump after this dead zone. The derivative has to be bounded at all points. It has to be continuously increasing. And then also, it has to meet a technical condition called being subanalytic. That basically means it's like a projection of analytic functions. But anyway, pretty much any nonlinearity you'd be interested falls into this category of things. Okay, so this is kind of a general threshold. Each of these thresholding functions gives us a different C, right, that we might optimize over. And what we can say is, like, look, where our complications come are basically, look, this thing's not continuous. That kind of interrupts a lot what happens in the sort of traditional switch linear systems analysis. The other problem is it's not bounded. That's also another a thing which doesn't allow us to just plug and play. And another thing which actually rules out a lot of stuff is, we're really interested in underdetermined phi. So there's kind of null spaces the state can move in that we have to ensure ourselves that we don't get oscillations that last forever. But anyway, what we can say is under these mild conditions, even if your solution is not unique, so here we have two columns being the same, if I start from anywhere, I'm going to converge to an optimal point. So we say even though, in this case, the solution is not unique, so it might converge at different points, it always settles down. It's not going to oscillate within this point. So that's comforting to know. It's not necessarily surprising that happens. You can also say things like, okay, I can view this thing almost like a switch linear system. So when things are activated, at least in the L1 case, and when I have nodes activated, basically I evolve just like before when we're moving along a piecewise linear path. Here, you're solving a piecewise linear system of differential equations. So I evolve like a linear system until something becomes active or inactive, and I evolve like another linear system. So you might ask, okay, first question you ask is, how many are the number of switches I make finite? And you can say under very mild conditions, yes, the number of switches you make are finite. This is just sort of a plot of the ratio of the number of switches you make versus the sparsity. So maybe you get something typically 1 or 2 or 3 times the number of switches. We'll talk about something more precise in 1 second. Okay, so the second thing you can say, which again, I don't know if this is really a result, but it's going to help us plug into what's next, is let's say we have these conditions for global convergence, and on top of that, say on every point we visit, the energy is preserved, right? So when we see properties like this in compressed sensing, usually we're talking about preserving, if we're talking about preserving the energy between all S-bar signals, we call this restricted isometry property. But basically what this means is every point along the path we visit, which we're not saying anything about yet, say energy is preserved, then we can say, it's not too much, it's actually pretty straightforward to show that you get exponential convergence with this architecture. Right, so then maybe the trick here is to say, okay, look, this result makes this assumption, or I know stuff like this is true if I have a phi which obeys my RIP, and I could make some guarantee about not too many sets becoming active at one time. Right, so that's also exactly what we can do. So one very strong result which requires very strong conditions is we can say the following. So let's say we start the circuit at rest. Right? We feed it some measurements of a sparse signal, and we assume this threshold is appropriate set. Then we can say, okay, let's watch this thing evolve and watch all these nodes become active. And let's say every time, what happens is I sort of uniformly add nodes that are part of my support and then finally settle to the solution. So every time I add a node, it's one of the right ones in the support, and then finally, after it has the right, it just evolves like a linear ODE and settles to the solution. So that will be true. I'll sort of add the right thing all the time if I have a compressed sensing measurement, sensing matrix, and say the number of measurements is like S squared times some log factor, right? So sort of very strong, non-optimal, but we see results like this for like OMP working in exactly S iterations in the literature, or for like the Lars algorithm taking exactly S steps as it moves from 0 to the solution. You see these same kind of things, and actually, you have to. It's different, but a lot of the analysis uses those same types of ideas. Okay, but if we're a little laxer and say, okay, look, I don't so much care if I'm adding the elements for the right support or not. Really, all I care about to get this exponential convergence to the true solution is that I don't add too many. That way I can say, like, if I have this restricted isometry property, it doesn't really matter where I am. As long as I don't have too many things active at one time, even if sometimes they're the wrong ones, I can still get exponential convergence. And in fact, under these weaker conditions, so if I have like a random compressed sensing matrix whose number of rows looks like S log n over S, so we know that sort of solving L1 will recover the vector in this case. And also we can say that, look, if we try to solve it with this LCA, the number of active nodes we see will never be more than twice the number that's in our original set, right? And that really says, okay, look, we have exponential convergence to the solution. Okay, so that's where I'll end. We had two sort of very different looks at dynamical L1 reconstruction. Here are some references that the talk are based on. I'll be happy to take any questions. Yeah, that's fair.